We'll now give a more substantial example. So that one can be clever and do this with macros, but we want to illustrate a bunch of concepts. It's not going to be a large amount of code, but with many very powerful concepts that Lean provides for metaprogramming. Our goal is to write a tactic rewrite LEH, which works if the goal is an inequality, A is less than or equal to B, between natural numbers, and H is also an inequality. And this tactic works if one of the ends match or both the ends match. If both ends match, it simply closes the goal. If one of them matches, it leaves the remaining piece as a goal to be achieved. Okay. Now, because this is complex enough, we split it into the two videos. And our first video is simply to recognize when the goal or the type of the hypothesis given, more generally the type of an expression or an expression itself, is such an inequality. Okay. Now this can be done in different ways. For example, Lean has very powerful helpers, okay, which can be used for expression.equality. So this recognizes when something is an equality, and if it is, it will return the type as well as the two sides of the equality. More general things you have, this itself uses something called expression.app3 question mark. The expression.app2 question mark is given a name. It looks if it's a function application with that as the function, that is a given name as the function, and two arguments. Now you would be tempted to try that with nat.le, but it's not going to work. It's not going to work because you see everything is heterogeneous or general internally in Lean, which is the, for example, just like hadd.hadd, we'll use our tool and see the expression for 1 is less than or equal to 2. It's going to be this heterogeneous le.le, okay, and which uses an instance of LE with natural numbers and specialized. So the expression you get is not going to be of this form. And in any case, even when you're dealing with equalities and options, if you get into more complex metaprogramming, you'll realize that this is too weak. Very often it doesn't match because the expression has not been formatted correctly, it's not been reduced, or some simplification is needed, etc. But that's a really nice, robust way of doing it, which is what we will see now. Okay, so let's write this function match LE. So it's going to have an expression, and it's going to return not an option directly, but meta m of, let me put it on the next line, meta m of option. Uh, we want to return two equalities, but we are not going to return the nats. We're going to return just expression slash times expression. So we are going to return. So let me just say sorry while I deal with the signature of this. Okay, so what is this supposed to be? So this is a matcher which, given an expression, checks is it of the given form, that is it nat.le between A and B, and if so, it returns expressions for A and B. The A and B need not be literals, they could be variables or any term at all of the correct type, the type being natural numbers. As I said, reading the expression doesn't work, but we'll do this using meta variables. Okay, so that's where meta comes in. There is a state. That state has all sorts of things, a local context, meta variables, etc. And we are not going to directly access it. It will be implicitly accessed. So it's really nice that it all happens in the background for us. So let's start writing the code, and the key point is to use meta variables. Okay, and this time we're really going to create them. Remember, these were fresh. These were supposed to be unknowns while solving a algebraic equation or something like that. So we will create these, and they are unknowns, and we'll try to get Lean to solve them for us. Okay, so we'll make fresh expression meta variables, but I want to have a type for these. Okay, so we just make the fresh meta variables. It doesn't need a context. But first, let's see what the type should be. We'll make const natural numbers. So with the name natural numbers. Okay, and we'll make a fresh expression meta variable with type this. And B is we'll make fresh meta variables expression mvar again nat. So what we have done is, just like in algebra, we create a and b as two variables. They're unknowns. We have said that their types are nat, and we are going to try to solve that. Well, what will we solve? Let's create an inequality. Okay. We'll use make appam. It's a function. We start with nat.le, and let's look at the inequalities a and b. Okay, so there was a issue here. Yeah, so a itself is a make fresh meta variable. They really did have to be meta and meta. I had not said nat or none there, that's why it was not at meta level. So here we have two meta variables, and we have their expressions, and we have an inequality between them. Okay, so what? How do we solve it? Well, there is this marvelous unification solver of Lean which is used heavily internally, and that is called isDefEq. Okay, so if slash L, this is how we call it, isDef equal inequality E, then let me just say sorry for now, else. Sorry. So let me just explain briefly what happens here. So is def equal to, you would think of as deciding whether things are definitionally equal. Yes, that's a highly non-trivial problem. And if that's all this did, it would still be extremely useful. But this is quite a marvelous thing. It does more than that. If either of the expressions have meta variables, or even both of them does, it tries to assign values to those meta variables so that the equality gets filled. So in this case, it's going to try to assign values to a and b so that the inequality expression will match E. Okay, and will match it at a definitionally equal level, not literal matching of the expression, which as we saw does not happen. So if it is not equal, then we clearly are going to return none. Okay, we are saying nothing happens. Okay. And if is the definitionally equal, well, then what happens is we return sum a comma b. So we return these values. Well, these values are not exactly magically changed. They're still meta variables, but they have something assigned to them, expressions assigned to them. So sometimes you have to be careful if you're literally matching expressions or deliberating and so on. But generally speaking, once a and b have something assigned to them, they behave like those expressions. So this thing has been solved. Well, let's see if we can solve it test this or illustrate it. For that, let's write a tactic. Okay, so we'll call that tactic match LE. This tactic will just do. Okay, so we'll match. So what we'll do is we'll take uh, the match LE of the main target. So we are saying if the main target is this, I don't need the parenthesis here. So what is this expression so far? So with sum AB to, let's fill it up. Let me just leave it as sorry here. Dash to sorry. In fact, none to sorry. That only two cases. So what we have done is we have got the main target and seen if that is of the form less than or equal to. Not a proof of, this is the target, so it should be of that type. And the tactic is going to do nothing. It's simply going to log accordingly. And now I have been saying log, but log goes into the info view, as you may have seen. And it is a message, and there are different kinds of messages. You could give a warning, an error, or just a message. Okay, so with this, it's going to be a warning if it does not match. So we can say main target not of the correct form. And in this case, let's give it some info. So let's get this into a different line. And in this case, we'll just log info. Okay, and we matched, yes, matched inequality. Okay, and A equals A and B is B. So we are going to, if we match the inequality, it will give you the values. And let's look at an example. Let's take two natural numbers, x, y, nat, and I want to show x is, let make it provable. So just like that, we'll take h is x is less than or equal to y, and I want to prove x is less than or equal to y. Okay, so let's get into tactic mode and let's look at match LE. And you get the inequality. So matched inequality, A equals X and B equals Y. Let's smooth this out with a space. And of course, the proof itself is assumption. Okay, so we have seen that our method works, and it works by solving these inequalities. Let's make a small variation of this. What if we want to match the hypothesis rather than just the goal? Okay, so match LE hype. Okay, and I have a term here. Okay, so in this case I don't want to get main target, so I'll get the hypothesis. So the hypothesis is obtained from this. So remember, we saw earlier that you have a T is syntax, and there is something called an elaborator which will turn T into which will turn a syntax into an expression. So indeed we have got an expression. Actually there are a couple of these. There's a elab term and there's a tactic.elab term. We are in tactic mode, so this is the one that gets priority. So we have an elaborator which has turned it into an expression. Okay, but actually the hypothesis itself should not be the inequality. Its type should be the inequality. So there is another method we are going to use. It's the infer type. So this infers type of an element. Okay. Oh, so I'm sorry. I still want match inequality, but instead of the main goal, I'm looking at infer type of h with this. Okay. So here, let's try to match LE hype, and well, it's giving weird errors because I haven't yet given its h. Once I give it h, of course, we have the matched inequality. Again, h has a equals x and b equals y. So this is what we are going to be using to match for h and the target. We won't use these literally the tactics, but the same match LE things, and then rewrite accordingly. That we will leave to the next video.